Welcome to the Journey Chez Chem. Please do the 2 warm-up questions to the best of your ability, and we'll go over them in a moment. Number 1 is the combined gas law. When we write a chart of the variables that were given in this problem, we realize that we have volume, pressure, and temperature. And remember, temperature must always, always, always be in Kelvin for gas laws. Now I'm solving for V2, my second volume. And here's my combined gas law. I always like to write it first the way I remember it, and then I solve it for my unknown. And therefore, V2 equals V1P1 over T1. And then to undo division, I multiply. And to undo multiplication, I divide. Then I know that I'm putting them in the right order. And then I substitute in the values. 10.6 centimeters cubed. And the pressure is 740 torr. And my T2 is standard temperature. And my T1 is 298 Kelvin. And I don't like that. Let me write it better. And my second pressure is standard pressure, and that would be 760 torr. And when I do the math, I get 9.4551. And then I know that I have to change it again to a different unit. But I want to go ahead and change this to the number of significant digits that I need, and that would be 3. I look at this 5, and it rounds the 5 up, and therefore it's going to be 9.46 centimeters cubed, and then I will change it. And I'm changing it to decimeters cubed. And I want to cancel centimeters cubed. And therefore, there are 10 centimeters is equal to 1 decimeter. And when I cube 10, I get 1,000. Centimeters cubed is equal to 1 decimeter cubed. And if I use a conversion factor, I won't make a mistake. But if I try to say, oh, well, do I multiply by 1,000 or do I divide by 1,000? Which one do I do? Well, conversion factor will always give me the right answer. And in this case, I'm dividing. And therefore, I get 0.00946. Or when we have lots of zeros, sometimes we want it in scientific notation, and that would be 9.46 times 10 to the negative third decimeters cubed. I'll write it right here. 9.46 times 10 to the negative third decimeters cubed. So those are potentially my 2 answers, although here I must put decimeters cubed. Always want our labels and our units. And that's how you do number 1. In number 2, we have a Dalton's law and a combined gas law problem. And we know this because it had a cow. It was collected over water. Now, just because we use cows to alert you that you have a collected over water problem, you may not see that on an assessment or on a quiz. However, you should be able to identify if you see collected over water that that is the same thing as having a cow. And that's just to help you learn a little bit there. But don't expect to see that on an assessment. So here we have a cow. And so I have volume, pressure, and temperature. And whenever I collect a gas over water, I must subtract the pressure of the water. You'll recall that the pressure of the dry gas is equal to the pressure of the total minus the pressure of the water. And we get the pressure of the water off of a chart at this specific temperature. And you'll recall that if water is boiling, then that means that the vapor pressure of the water is equal to the surrounding pressure. And at 25 degrees Celsius, the pressure of the water is 3.2 kPa. And therefore, I get my pressure, my P1, which is the pressure of the dry gas, is 96.3 kPa. And then I have 25 degrees Celsius that I changed to Kelvin, and I'm changing these to standard temperature and pressure. Then once I have Dalton's law using my P1 to get my P1, then I'm going to use the combined gas law. And I'm going to solve it for my unknown. And my unknown is that V2 equals V1 P1 times T2 divided by T1 P2. Now I will substitute in the values from my chart. And I have 150 milliliters. My initial pressure is the 96.3 kPa. And my second temperature is 273 Kelvin. That's standard temperature. And my T1 is 298 Kelvin. And my P2, have to look at my equation to see which one I'm putting in there, is 101.3 kPa. Remember, we must use the one that is consistent with our units of pressure, so we're not changing that. And when I do the math here, I get 130.6334 milliliters. Now, I know that I must make another conversion, but I'm going to go ahead and put it in the right number of significant digits, which would be 3 when I look back to my original problem. The number with the least number of significant digits is 3. And therefore, the 6 rounds the 0 up, and I get 131 milliliters. Now, I must make a conversion, and the conversion is to meters cubed. So the first thing I'm going to do is change my milliliters to centimeters cubed. And I know that 1 centimeter cubed is 1 milliliter. And I'm going to meters cubed, and I'm going to cancel centimeters cubed. Now I know there are 100 centimeters is 1 meter, and when I cube 100 times 100 times 100, I get 1 million centimeters cubed is equal to 1 meter cubed. Now when I do the math here, I'm going to have lots of zeros, so I prefer to use scientific notation. And this is the same as 1.31 times 10 to the 2. And 2 minus 6 is minus 4. And therefore my answer is 1.31 times 10 to the minus 4 meters cubed. And that's the answer to number 2. Now, I'm really excited now because I'm going to show you Charles's law, and I'll see you in the lab. Here we are in the lab. I know you're as excited as I am. Well, the first thing I get to do is light the Bunsen burner. But before I do that, let's talk a little bit about what's going to happen. I have a soda can, and I'm going to put a small amount of this icy water in here. And therefore, when I heat this up, I'm going to drive out the air that's room temperature in there and replace it with warm air. And that would be warm gases. And we are going to then change the temperature of the gas, which is 373 Kelvin. It's approximately 100 degrees Celsius in there as the water is boiling. And then I'm going to quickly put it into this icy cold water. And that is going to drop the temperature very quickly. Now we know that volume and temperature are directly proportional. So as I lower the temperature, I'm going to do what to the volume? Well, you'll just have to see how that works. Probably know before I even do it what's going to happen because you know the relationship. So let's see how it works. Well, now I get to light the Bunsen burner. You know I love lighting the Bunsen burner. Here we go. Sometimes it's a little trickier than others. Well, that was just fine. Now I have to hold this so that I can quickly flip it. So I'm going to heat this up and let it warm up in there, and I want to see it boiling in there vigorously, steam coming out here. And remember, we know that volume and temperature are directly proportional. Therefore, I'm heating this up, so I'm starting with a high temperature inside, and I'm going to quickly lower that temperature. So as I lower the temperature, we'll see what happens to the volume. I want to make sure that it gets nice and toasty in there. You can see the steam coming out. Are you ready? Here we go. Quick! Woo! Did you see that? Look at that. That's just amazing. You just gotta love that. So there we have Charles's Law in action. So that way I showed it to you. You don't have to just believe me. You can see it in action. Well, this evening you have some problems and they're all mixed up. And that's what you're going to need to be able to do on the quiz in a few days. Well, I know you can do that, no problem. And I can't wait to see you tomorrow.